and it is a pointing. Actually, it is not a group. It is just a pointed set, and pointed by the class of the trivial G torsor, which is just G with the right multiplication on itself. So the very basic example, or first, if we take the orthogonal group On, then the set of H1 K On classifies the isometric classes of quadratic forms of rank n over Kn. And a second basic example is when PGLN is a projective linear group, the set H1K of PGLN classifies the central-sepal algebras of degree n over K. And thus, in a general, we can define a functor H1 star G, which go from the category of field extension of little k to the categories of set. And so now let's define what is a cohomological invariant. So let G be an integer, M a Galois module for little k. And in general, we can define the functor HD star M from the category of field extension to the category of abelian groups. As the definition that the formal definition that comes from Serre is that a degree G cohomological invariant of G with coefficient is M is a natural transformation from the functor H1 star G into the functor HD star M. And more precisely, that is a cohomological invariant is a collection of maps from H1KG to HDKM for every K in a K extension, capital K extension of K. And we ask that all these maps are coherent together, so that they are factorial in capital K. So in the notation we will use is that invdgm is an abelian group of degree D cohomological invariants of G with coefficient is M. So here, as HD of Km is a group, we can add cohomological invariants together. This is why we have an abelian group here. And in this group of invariants, we have a special invariant that is the normalized invariants, which are invariant I, such that on the trivial G torsor, the invariant is 0. And this enables us to actually to decompose a group of invariants with the normalized invariants and the constant invariants, which don't break any information. Actually, it's just the cohomology of M. So this is another problem. It's not related to G. So in general, we forget him. We forget it. I'll precise that for the normalized invariant subgroup, I put 0 here instead of the whole group. So the most basic and important example offers the Galois module Z over 2 when the characteristic of the field is not 2. Then a more general example is when we take M, the tensor product of the n roots of unity for n for a good n, so that is a coprime to characteristic of K. And another generalization of that case is when we talk about Q over Z of D minus 1. The D minus 1 is like a torsion of the first module. And basically, it is defined as the sum of well, all the n roots of unity for Q prime co-prime to the characteristic. And for the P torsion of this module, we need to define here. This is Kato. You can sometimes it's called the Kato module, or in more generality, we have to use the pro-complex of Duran-Witt differentials. So it is more complicated than the torsion when outside the characteristic of K. And I won't define it, but this is an analog of the module of n roots of unity for the characteristic. So Q over Z of D minus 1 is a Galois module here for little k, and it is also defined as a Natal sheaf for every K scheme. And one has a particular case of that for a field H2 of L QZ of 1 is canonically isomorphic to the Brauer group of the field. And this is why for the rest of the talk, I will say invariant of, for instance, of G, Brauer 0 or not 0. This is just cohomological invariant groups of, this is just a group of cohomological invariants with coefficient in of degree 2, with coefficient in Q over Z of 1. And now I will state a very basic example of cohomological invariance. So we take M to be Z over 2. The characteristic of K is not 2. And we define the Stiefel-Whitney invariance, which is as follows. For Q in a non-degenerate quadratic form of rank n over capital K, we write Q as in a diagonal form, so with coefficient A1, AN, and we put WG of K to be the sum of all the indexes of the coefficient, and we take the product of the coefficient. Here the coefficient, just one coefficient is in H1, and if we take their product, we are in Hg of K Z over 2. And well, we have to show that this is well defined, and for that is it doesn't depend on the form on the isometric class of Q. And well, this is possible, but I won't talk about it. So one gets a map WG from H1 of K into Hg of K Z over 2, which maps the class of Q to the invariant just above. And all these maps for capital K, we can put them together to get a degree G cohomological invariant of the orthogonal group with the coefficient in Z over 2. And now for the rest, I will just test some non-results. First, a result related to the Stiefel-Whitney invariant. So this is a theorem from Serre. So for quadratic forms, if we take the direct sums of the degree G invariant of ON, and we see it as a ring for the cup product, well, we get a free module generated by the Stiefel-Whitney classes WG with coefficient in the constant invariant, so the cohomology of the base field. And this has as a consequences that we can describe degree 1 invariant. So it's just the sum of here the constant invariant and the invariant W1, and the same for the degree 2 invariant. We can continue for all degree. So then in general, if just before it was the case of quadratic form, but in general, in degree 1, for every torsion Galois module M, if G is a smooth connected linear algebraic group, then the degree 1 invariant has no non-trivial normalized invariant. I mean, there is a 0 here. So every invariant actually is constant. Then in general, also in degree 2, we have a theorem from Blinstein and Merkurjev, which is that for G assumed to be reductive when the characteristic is positive, there is an isomorphism of the group here. I call it the normalized Brauer invariant, and it is isomorphic to the Picard group of G. So and here the restriction are so we assume G to be reductive for a positive characteristic, and also we don't have at first we don't have a naturality of the isomorphism. So I will come back later. And well, to finish the introduction, I'll talk about degree 3 invariant. So this is this comes from Rost. For G, an absolutely simple, simply connected group. So over any field, we don't say anything about the field. The normalized degree 3 invariant of G with coefficient in Q over Z of 2 is a finite cyclic group, which is generated by the so-called Rost invariant. And well, there have been many generalizations. So first, for every semi-simple groups, this result, I mean, is not that simple. We have an exact sequence, but by Merkurjev. And then for G torus, there is also in Blinstein Merkurjev an exact sequence that in some sort generalize this theorem. And for every split reductive groups, there is a generalization by Lachman-Merkurjev, and these generalization have pretty much all the same forms. They put the degree 3 invariant in an exact sequence, and the many terms of the sequence are very similar. So I come to explain the result I have. So we take K to be a field, and we put no restriction of K. So it may be finite or infinite. It may be of any characteristic, and it may be perfect or not. But actually, what the result I have are only useful when the field K is non-perfect. Otherwise, It has been done by Blinstein and Merkurjev mainly. So we take G to be a smooth and connected linear algebraic K group. And well, I recall the notation that X1 of GGM, this is a group of extension of G by GM and equipped with a bare sum. And the result is that we have an isomorphism natural in G from the extension group to the normalized invariant, Brauer invariant of G. So then once we have this formulation, I make some remarks on the extension group. So we recall that one has a canonical homomorphism from X1 to the Picard group of G. When G is reductive or the field or the base field is perfect, one has an identification between so X1 and the Picard group. And in that case, we recover Blinstein and Merkurjev's result by changing X1 by the Picard group. And also in that case, the group Pj is finite, whereas we will see that X1 are actually maybe infinite. To continue on the finite case, we recall that a result by Gaber-Rosengarten that if G is unirational over the separable closure of the base field, then the extension group is isomorphic to the Picard group, and also the Picard group is finite. But in general, we have no, the canonical morphism is not an isomorphism, and even the extension group can be infinite. So they are many examples of unipotent groups with X1 infinite, and we can find them, for instance, in the HS paper, Rosengarten, or Totaro's. These are different papers, but they are other ones. This. And it is easy to show that in the case of unipotent groups, X1 of GGM is always a P primary tension group. So in that case, if we look at the above theorem, there won't be any element, any invariant of torsion other than P, than primary to P. And after some remark, I recall a classical construction for Brauer invariant. That is for any field extension and for any group extension of G by the GM is a multiplicative group. I forgot to mention it. Well, if we take the if we take the Galois cohomology, we have a connecting morphism from H1 of Kg into H2 of Kgm, which is the Brauer group of K. And so if we define just the general map phi G from X1 to the group of normalized Brauer invariant, which sent an extension to the connecting map without the field with indeterminate with all the field together. Delta E dot is a collection of all delta E K. Well, the result is that for every smooth and connected linear algebraic group, this classical construction is gives an isomorphism, and well, that was not obvious, and actually this is a corollary of the theorem above. And well, actually, for this proposition, we need the naturality of the isomorphism in the theorem. So we have also an explicit calculation for the group of invariants in some new case. So if we take a finite extension of little k, which is purely inseparable, and we call h the least integer for which k prime p power h is in k. So I call it the high of the extension. If we take G prime to be a semi-simple, simply connected K prime group, and if we take a central subgroup mu prime, so which is a finite multiplicative group, we call a mu prime hat the character group of mu prime, and the result is that for G, the veil restriction of G prime of mu prime, or G, the quotient of the veil restrictions, one has that normalize the group of normalized Brauer invariant is isomorphic to p power h and mu prime and the character group of mu prime. And so explicitly in the case we take G prime to be SLPN and mu prime to be mu PN. One has that the group of invariant is a subgroup of Z over Pn generated by pH. So this leads to two remarks. First, well, there is only P primary torsion. And the second is that if H is large enough, there is no non-trivial normalized invariant for G. So the fact that we looked at such a group is because the starting point of my thesis was to study the invariant of pseudo-reductive groups. So these are some pseudo-reductive or pseudo semi-simple groups. So now I will talk about what is useful to study to get the result, the theorem I had. So first, let's talk about versal torsor. And if we take G smooth and connected, and we take an embedding, a group embedding of G into GLN, then we can form the quotient map psi from GLN to GLN over G. And we recall GLN U and GLN over GX. And this is a G torsor. And also this torsor is what we call a versal torsor, because in a sense it contains every G torsor of any field. That is that for any extension capital K over K and any G torsor Y over K, there will exist a capital K point of X, such that the G torsor Y is the pullback of the general torsor Xi through F. So we have a Cartesian diagram here. And so this is a versal torsor because the morphism Xi classifies all G torsors of fields. And then when we have the G torsor U to X, we can define following Serre Merkurjev, we can define two morphisms from the Brauer group of X to the group of Brauer invariants of G. And also we have the identity map from the group, I will explain. So the second group is here the sheaf here is a sheaf associated to the pre-sheaf on X, which associates to V the étal group of the H2 of V Q over Z of 1. And well, the indexes, well, means the subgroup of balanced elements, and well, it is a condition to so that the two maps are well defined. But, I will not go into it. Just to explain the two maps here, well, we take, for instance, for the first map with the Brauer group, we take alpha in the balanced subgroup of Brauer of X. For a G torsor Y over capital K, we choose a point of X so that Y is isomorphic to the pullback of the general torsor Xi. Then, thanks to that F, we have an induced map on the Brauer group from Brauer X to Brauer K. And we just evaluate the element alpha through that map. And we put, so I alpha of Y equals to F, the pullback of alpha. And well, we need to check, and actually the balanced condition, this enables to define I alpha as a whole invariant of G into the Brauer group. So, and well, the same works for this other group, because in that case, when X is a field, we just have the Brauer group of the field. And one important point is so a theorem by Blinstein and Merkurjev is that the second map, if we construct the map like this, well, we get an isomorphism of a group. So every Brauer invariant of G well, comes from a unique element of. So this group is actually the unramified unramified element of X in I mean in H2. Well, never mind. And we have another, well, besides this versal torsor, we can define another kind of general torsors, and well, I called it the simplified classifying torsor, and this comes from Delim. I mean, I never. This is the first time I saw it in Delim. And we need simplicial schemes. So we define first for given G, we can define the simplicial scheme EG, which has as component all the product of G, and with the canonical maps between them, like we forgot a coordinate, or we add a one. we are, I mean, like, between the component g n plus 1, we forget some coordinates, or we introduce sometimes a neutral element to fill the gaps. And on this simplicial scheme, well, we can make G act on the right, and when we take the quotient, well, we obtain the simplicial scheme BG point. And in the sense of simplicial schemes, EG point will be a G torsor over a BG point. And actually, it is a more general G torsor in the following sense. So if we take any other G torsor Y over Z, well, it is possible to associate a simplicial scheme YG point such that there is a straightforward morphism from YG point to BG point. This is the equivalent of, the equivalent point of view of for versal torsor. Here we take a point of BG, and the torsor YZ will be like the pullback of EG over BG through this map. And an interesting case of cohomology of simplicial schemes is that if we take the degree 2 cohomology of YG point with coefficient is GM, we recover the cohomology of the base Z. And thanks to this construction, we can define a morphism from H2 BG point GM into the group of Brauer invariants as follows. So this is mainly something I find in Enokan, Levin, Viveg papers on the Aronson invariant. And we proceed as a versal torsor case. So if we take an alpha in H2, and if we take a G torsor of a capital K, well, so we have these two maps. So we can compose with the map from YG point to BG point. We have the pullback map between cohomology, and secondly the cohomology of YG point is just the cohomology of K, which is the Brauer group of K. And well, in that case, it is easy to check that the J alpha of Y doesn't depend on the isomorphism class of Y. So we can define a global invariant J alpha in the, we can define the Brauer invariant of J alpha. And so at these points, we have three morphisms. So one has we have three morphisms into the group of Brauer invariants of G. So first, the cohomology of the simplicial classifying space BG point. Then from the balanced subgroup of Brauer of X. So here X is the same as before. So this is just GLN over G. And the same for this group. And actually, these three morphisms, we can, well, they are related. such a diagram. So first, the map from H2BG point factors through the balanced group of Brauer X, and also from the unramified cohomology of X. Well, we can go directly to the group of invariants, or we can go through the Brauer group of X. And well, I labeled the morphism. So here, I mean, first, actually, the map 4 is an isomorphism, as I recalled the Blinstein and Merkurjev theorem, and and we can see that thanks to Gershen's conjecture, the map 3 is an isomorphism. And we can find an isomorphism between the two. And so we are in the situation where the map from H2BG point to Brauer X to the group of Brauer invariants. Well, we have first an isomorphism here because because 3 and 4 are isomorphism. And here we just need to get the theorem with the extension group, we need to evaluate H2 and show that 1 is an isomorphism. And for this, well, we write Brauer of X as a cohomology group of UG points, so with U equal GLN. And we have a spectral sequence, the convergent spectral sequence for simplicial schemes, which relates all the part of the simplicial scheme to the whole cohomology. And well, we can calculate to obtain that what we wanted. So the cohomology of BG point, I mean, over the constant subgroup is isomorphic to the extension group of G, and is also isomorphic to the balance group of Brauer X over the constant still. And so by composing, we have a morphism X1 to the normalized group of Brauer invariant. And well, also we need to check that this is natural in G, but well, this is mainly from the naturality. G comes from the naturality of the composite here, and also of the spectral sequence here. And I mean, it's a little short, but thanks.
So you use these simplicial constructions, but one could also just think of BG as the stack, the classifying stack of G torsors, and like a lot of what you said is still true.
Yeah, I guess,
but what is the advantage of these simplicial constructions, or should this work even when you take the approach of quotient stacks?
But I mean, I'm not sure this is like better than stacks. But well, at the time I didn't really know a lot about stacks, and well, they were literature for. I mean, there is the article by Deling, Hodge theory, like 2 or 3. And this was clear.
Okay.
I mean, I had nothing to add to what was made. So.
And
but yeah, I'm sure it should work with stacks, but I don't know.
And so I have a second question that it's a bit more general. So if one has a quotient stack, but I imagine also something constructed with these simplicial methods in general, like x over g. So as long as we are outside of the characteristic of the field, this isomorphism between like the L torsion of the Brauer group and the cohomological invariants in an appropriate sense, the unramified cohomology with coefficients in Z model shifted by 1 is still true. But do we? So and in your case, it also extends to the bed prime, but
but actually, yes, this is I mean, the P torsion for the characteristic is a delicate point, because otherwise a lot of things are easier with outside the characteristic. Like first, even for the Brauer group, even for a field, when we want to define it at the Galois cohomology group of the roots of unity, there is a problem with the P torsion. We have to use Kato differentials, and there are other methods with outside the characteristic, because the cohomology of like a mu n for n co-prime to P, it is like homotopy invariant, and we have well, it works better to calculate. I mean, the main point of the talk is the P torsion, because otherwise I don't tell nothing new. So.
Yes, no, but what I mean, this reason why these isomorphisms extend to the P torsion, like I understand that this is the important part, but is it very like group theory specific, or is it like more like an effect of the general equivariant construction? Because I was wondering if, in general, if we have something. So maybe Bert can answer this question. If in general we have some quotient x over g, where we
but I mean,
P torsion of the Brauer group, and these are different, or if we should think that they should be equal in general.
Yeah, I'm not sure to understand the problem. So,
I mean, there's a lot of different things you could ask. Like for example, I mean, you might say how many of the steps that you do extend to like higher cohomology. You know, there are all these different groups that you can try to compare, not just for H2, but for higher cohomology, like the simplicial scheme and the invariants and so on. I don't know. Is there anything you can say about like some things work? In other words, why H2 specifically in your arguments?
Here, like for the isomorphism 3, no?
Well, for sort of all the steps. I mean, are there some of the steps that work, you know, in higher degrees?
I mean, I'm not. I mean, I don't really understand what
the point. The question is, I mean, sort of, you know, there are all these different ways that you could try to understand cohomological invariance in higher degrees, like using the simplicial scheme, or you know, and I'm just wondering. So, in some sense, you show that all the approaches give the same answer for H2. But, you know,
in higher degrees, like the isomorphism. I mean, it's more delicate to evaluate the unramified cohomology. Here in degree 2, well, happily we have an isomorphism with a common Brauer group, but in higher degree, I mean, there is no. Maybe it's not that nice.
But at least there are some maps, right? I mean, so there should be like a.
Hello?
yes.
Yeah, I have a question about this isomorphism tree. So if you look at the prime to p part, it's okay.
Yeah,
But for the p part, you're saying the Gaston conjecture. Now the p part you want in the Brauer group has to do with differentials. So which kind of Gaston conjecture are you using there?
Yeah,
I mean when you use unramified cohomology and you think of the Gaston conjecture, you're using a purity theorem. Basically, you're saying that if you take a smooth variety X and you take an open set whose complement is of codimension at least 2, then the Brauer of X is equal to the Brauer of U. And here you want it for the p part in KFC.
Yes. This is, I mean, because this is the Gaussian conjecture that for like for mu p.
No, but it's not. No, when you define the, I mean, in Cato, it's not mu p which is used. It's this different. It's this various things with the differential, the fish sheaves.
No, this is like the Doran-Witt differential, but I mean for the perfect field case.
Yeah.
This go from gros to.
Yeah, that's right. That's right. You have to use. Okay, you're using this. You're using this. So fine.
Yes, the version. Yeah, for.
All right, you can use that. Yeah, that's okay.
This is it.
More questions?
So I'm sorry if you addressed this somewhere in the talk and I missed it, but in your hypotheses on G, in the statement of your theorem, you take G to be smooth and connected. Could you give an indication, if it's not prohibitively technical, where these sort of conditions come up in the structure of your argument?
Actually, it was, I mean, connected. I don't know, it was like maybe to not bother with other aspect of torsors, but and for the smooth part, well, it is to, like, for instance, this construction is stated for a smooth group, I think.
Oh, but okay, that one in my paper, I checked that works also for, without smoothness. So the Blinstein and Merkurjev result, that's okay without being smooth. So maybe you can.
Okay. Yeah, I guess I mean I still need to see like for the non-connected case what change. And I mean also this is when I do calculation with a spectral sequence in the isomorphism. I mean I use like a result by a Sansuk, and it is stated for geometric integral scheme. So because we yeah, no, I'm not sure.
Okay, so more questions, comments?